To contribute to the energy transition was my motivation to start this project on power electronics for future grids.
Global warming has dramatic impacts on the ecological balance, biodiversity, as well as the economic and political stability of our planet. One of the most obvious examples in Europe are the melting glaciers in the Swiss Alps.
We want to have a solution which increases the controllability of the grid in an existing grid infrastructure. So we do not want to abolish the whole grid and substitute it, but we need something which fits in.
A transition from fossil to renewable power generation is a key step in reducing CO2 emissions and fighting climate change. However, the fluctuating nature of renewable energy generation reduces the power quality of the grid. If more and more renewables, such as photovoltaics or wind power plants, are installed, the grid voltage leaves the permissible range. A fast and dynamic grid voltage control is required. Advanced power electronic solutions are especially suitable to compensate such voltage fluctuations.
To demonstrate the potential and the functionality of our concept, I optimized and realized a 100 kVA hybrid transformer prototype system which interfaces the 20 kV medium voltage grid and the 400 volt low voltage grid. The hybrid transformer is a combination of a robust and efficient conventional transformer and a dynamic and flexible power electronic converter. The power electronic converter is rated at only a fraction of the conventional transformer. This is sufficient to keep the voltage of the grid in the required limits, even if a high share of renewables is installed. To adjust the grid voltage, one side of the converter is connected in series to the low voltage winding of the transformer. The other side is connected to an auxiliary winding to equalize the power balance of the converter and to compensate reactive power if desired. The converter of this prototype is based on state-of-the-art gallium nitride switches. This allows us to achieve a compact and efficient design even without fans for cooling. However, integrating these tiny and sensitive devices into the overall system was challenging. Today's grid is a rough environment for power electronics. We have significant overvoltages and overcurrents, for example caused by lightning strikes and short circuits. To make the hybrid transformer ready for the grid, one focus of my research was the development and the integration of a comprehensive protection concept.
Power quality problems are not restricted to the low voltage distribution grid.
In medium voltage grids, different overvoltage and overcurrent characteristics are experienced due to different grounding methods and different grid topologies. Simulations are performed to validate the mathematical models of such a converter, and then they are used to optimize that model in order to obtain a reliable and efficient converter. The Plex simulation environment is used, which is pretty common for power electronics converter simulation. By executing the simulation here, we can see the simulated voltage which is applied by the converter to the grid. And you can see a step change here, and this is exactly one of the applications used in a hybrid transformer where we want to support the grid voltage at its nominal level.
If I look at the system, I see a lot of work which I did and a lot of challenges we solved in the recent years, and it's great to see how now every puzzle piece comes together to create one system which could eventually solve the problems in the future grid.